Okay, in this video we're going to do several problems involving writing Taylor polynomials. And this first one we are going to do is involving writing a Maclaurin polynomial. And we spoke about that in the last video. If you have any questions about how this particular formula was generated by Brooke Taylor, an old mathematician, you can look at the video on the proof of the Taylor polynomial. But we're going to assume that you understand how this formula was generated, and we're going to use this to write polynomials that will approximate certain functions, and you'll see the value in this. So let's jump in. Find a Maclaurin polynomial. Now, a Maclaurin polynomial is a special version of the Taylor polynomial that is centered at 0. So let's write that in here. This is going to have its center at x equals 0. Now let's talk about what that means. That just basically means that this polynomial that we are going to write is going to be extremely close to the real function for values at 0 and around 0. Now obviously our goal is to make a polynomial or write a polynomial that will be very close to the function at all values, but centering at 0 guarantees that at values close to 0, our polynomial should be very, very close. And we're going to see that in just a moment here. So find the Maclaurin polynomial. We need f of 0 plus f prime of 0, x minus 0, because our c is 0. So let me write that in here so we don't get confused. Our c is 0 for a Maclaurin. So the best way to do this is just simply to write several things down here. We have our regular function f of x, which is sine of x. And we're just going to take several derivatives of this. We need it to be the 5th degree. So that means our last term needs to have an x to the 5th in it. So that's where we're headed. So let's just take several derivatives here. F of x is sine of x. F prime of x is cosine of x. And f double prime of x is negative sine of x. F triple prime of x is negative cosine of x. And the 4th derivative of x is, well, the derivative of cosine is negative sine times that negative is going to be positive sine x. And then you can see the pattern is going to start over again. So that's the first column that we will generate. And then next we're going to plug in our values for our center, our c. And so f of 0 is the sine of 0. That's going to be 0. Let me write that a little bit better. F of 0 is 0. F prime of 0, well, we're going to plug 0 into the cosine function and we get 1. F double prime of 0 is negative sine of 0 is just 0. F triple prime of 0 is going to be negative 1. And the 4th derivative of 0 is going to be 0. So the pattern is 0, 1, 0, negative 1, 0. So now we're just going to plug this into our polynomial. So we're going to call this P5 of x, which is a 5th degree polynomial, meaning our last term has to be x to the 5th. Now it doesn't mean that there's 5 terms. It just means that the last term must have x to the 5th as its power. So let's plug in. F of 0 is 0, so we don't write anything down for that. F prime of 0 is 1, so our first term is going to be 1. And then we have an x minus c, but our c is 0, so 1x. And then plus our second derivative evaluated at 0. Well, our second derivative is 0, so that's going to be, this whole term is going to be 0 because the second derivative is 0. And then the third derivative evaluated at c is going to be negative 1. So that's going to be negative 1 times x. And if it had a center other than 0, it would be x minus that center. But this is just a Maclaurin. So it's going to be x minus 0, or just x, cubed over 3 factorial. And then the next derivative is going to be the fourth derivative, which is 0. So that's going to cancel that term out. And then the next one is going to be the fifth derivative, which is going to be the same as the first because the pattern starts over again. So that's going to be plus x to the fifth over 5 factorial. And you can see that it's going to be a positive and then a minus and then a positive and a minus if we were to write it out more terms. All right, assuming we have found our fifth degree Taylor polynomial, or Maclaurin polynomial that is, we want to actually see how close our polynomial is compared to the real function. So we're going to plug 1.2 into our Maclaurin polynomial and let's see what we get. So that is going to be equal to 1.2 minus 1.2 cubed over 3 factorial plus 1.2 to the fifth over 5 factorial. And that actually comes out to be equal to 0.932736. Now, if we take 1.2 and actually plug it into our function, sine of 1.2 in radians, that is, we are going to get this answer, 0.9323908597. You get the point. It's a long number. All right, so the error in your approximation is the absolute value of the real function's value minus the approximation. So when we calculate that, that's going to end up giving us 0.0006969. So you can see that our approximation is very, very close to our original function. Okay, here in example 2, we want to find a Taylor polynomial of degree 6, which means our last exponent needs to be x to the 6th, so we need to keep that in mind. And our function is natural log of x. Here, it is not a Maclaurin polynomial. We want to center it at 1. The reason for that is, well, one of the reasons is that natural log of x does not exist at 0. And so we want to center it at 1. So we're going to just start writing down all sorts of derivatives. F of x is equal to the natural log of x. F prime of x is equal to the derivative of that, which is 1 over x. And then f double prime of x is negative 1 over x squared. F triple prime of x is going to be, well, if you take this x squared up to the top, that's going to be x to the negative 2. And you do the power rule, that negative 2 times negative 1 is going to be positive 2. You subtract 1 from the power, so that's going to bring the x cubed back down. And then the fourth derivative is going to be negative 6 over x to the 4th. And then the fifth derivative we'll put here. And that's going to be positive 24 over x to the 5th. And then the last derivative we'll put here, and that is going to be the 6th derivative. And that's going to be negative 120 over x to the 6th. Now what we want to do is we want to plug in our center into all of these values. So we need to find f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and this should say 1, f triple prime of 1, the fourth derivative of 1, the fifth derivative of 1, and the sixth derivative of 1. And that's going to give us our coefficients for this Taylor polynomial. So plug in 1 into the natural log. Natural log of 1 is 0. And then f prime of 1 goes here, so 1 over 1 is 1. f double prime of 1 is going to be negative 1 over 1 squared. That's going to be negative 1. And f triple prime of 1 is going to be 2 over 1, which is 2. And then the fourth derivative of 1 is negative 6. Our fifth derivative of 1 is 24. And our sixth derivative of 1 is negative 120. So now we're going to take all of these values and plug them into our polynomial. So we're going to call this our sixth degree polynomial. And that is going to be f of 1, which is 0. We don't have to write it, but I'll write it there. Plus f prime of 1, which is 1, times x minus c. And c is 1. So there's that. And then plus f double prime of 1, which is negative 1. So that's going to be negative 1 times x minus 1 squared over 2 factorial. I want you to notice something here. The power and the factorial are going to match up. So x minus 1 squared and 2 factorial and the derivative number. So notice that second derivative, second factorial, second power. They all match up. So the next one is going to be the third derivative, which is 2. So that's going to be 2 times x minus 1 cubed over 3 factorial. And then the next one is going to be, we'll just continue down here. It's going to be minus, the fourth derivative is negative 6. So that's going to be negative 6 x minus 1 to the fourth over 4 factorial. And then we're going to have positive 24 x minus 1 to the fifth over 5 factorial. And then the last one will be minus 120 x minus 1 to the sixth over 6 factorial. Now you can go through and cancel all sorts of things out and you will get a much cleaner Taylor polynomial. So let's go ahead and do that. The sixth degree polynomial will end up being, the 0 will go away, and the first term we have is going to be x minus 1 to the first. And then we have, I'm not going to write this minus 1, but 2 factorial is just 2 times 1, so that's going to be minus x minus 1 squared over 2. And then here we got to do something a little clever. 3 factorial, maybe I'll do that in a different color. 3 factorial is the same as 3 times 2 times 1. 2 times 1 will cancel with that, and then we're left with simply 3 on the bottom. So that's going to be plus x minus 1 cubed over 3. And then we can do something again with this 4 factorial. 4 factorial, let's get rid of that. Let's write that as 4 times 3 times 2 times 1. Well, 3 times 2 times 1 is 6. It's going to cancel off with that, and I think you can see the pattern. It's going to end up being negative x minus 1 to the fourth. The only thing that's left on the bottom is that 4 right there. So it's going to be 4. And then the next is going to be x minus 1 to the fifth over 5. And then the last term is going to be x minus 1 to the sixth over 6. And there's your sixth degree Taylor polynomial for natural log of x. All right, example 3. Here we are given the value of g of 2 along with the value of several derivatives of some function g. And it wants us to write the Taylor polynomial of degree 3 centered at 2. So that means we're going to plug into our formula. So we need our p of 3. So third degree polynomial. And that's going to equal f of, or g of for that matter, f of 2, which is 3. They give us that. And then we're going to take f prime, or g prime of 2, which is negative 4, times x minus where it's centered at 2, so x minus 2 squared, or no, just actually not squared. And then the next one is going to be f double prime of 2, which they give us that. That's 7. That's going to be 7 over 2 factorial times x minus 2 squared. And then the last one is going to be g triple prime of 2, which is negative 5, times x minus 2 cubed over 3 factorial. And there's our Taylor polynomial of degree 3 for this function g. Okay, this next problem, example 4, can be a little tricky, but let's see if we can work through it. It says that we're basically now going backwards from the problem that we had before. So it says they're giving us the third degree Taylor polynomial centered at x equals 4. And it says find the value of f of 4, f prime of 4, f double prime, and f triple prime. Well, f of 4, let's just circle that. That is going to relate to this term right here, which is going to relate to that term. So f of 4 is simply 2. Now, f prime of 4, I'll use a different color for that. F prime of 4 is going to relate to this coefficient in front of the x minus 4 to the first power term. Well, notice there is no term where it's x minus 4 to the first power. So therefore, that lets us know that f prime of 4 must be 0. And so then now we will look at f double prime of 4. So f double prime of 4 is going to be this value right here. And the coefficient is going to be negative 5. So this is where it gets a little bit confusing. Negative 5 is actually equal to this entire term. Negative 5 is the entire term, but they're only asking you for f double prime of 4. So what you need to do is you need to take f double prime of 4 divided by 2 factorial, and that is what is equal to negative 5. Hopefully that makes sense. The negative 5 is the number in front of x minus 4 squared. And the part that is in front of x minus c squared includes f double prime of c over 2 factorial. But they're only asking you for f double prime of 4. So 2 factorial is 2. Multiply both sides by that, and you get f double prime of 4 is negative 10. And we need to do the same thing for f triple prime. So f triple prime of 4 is going to be this piece here. And we see that 8 is the number in front of x minus 4 cubed. So 8 must be equal to this entire expression there. So why don't we say f triple prime of 4 over 3 factorial, and 3 factorial is 3 times 2 times 1, which is 6, and that must be equal to 8. So we multiply by 6, and we get f triple prime of 4 equaling 48. And now we can answer part B. Does f have a local maximum, a local minimum, or neither at 4? Well, this is where we're going to have to use our second derivative test. And if you can remember, second derivative test basically says, first and foremost, we must have a first derivative that is 0. Well, f prime of 4, as we denoted in part A, is equal to 0. So that means that there is some either a maximum with 0 slope or some minimum value with 0 slope, more than likely. And now the question is, which one is it? Well, that's when we learned the second derivative test tells you concavity. The second derivative is of 4, right at 4, is negative 10. So that tells us that this graph, because the second derivative is negative, it's going to be concave down. And if it's concave down, we're looking at something like this, which means there must be a maximum. So that means that f of 4 is a max. For the sake of time, we're going to skip example 5 and move on to example 6. So it says, what is the coefficient of the x to the third term in the Taylor series polynomial for 1 over 1 plus 2x centered about x equals 0? So this is once again another Maclaurin series, or Maclaurin polynomial rather. And so let's just start with, we have our f of x, and that is 1 over 1 plus 2x. And we can write that as 1 plus 2x to the negative first power. And that's going to help us when we do our derivatives. So f prime of x is going to equal, well, we can do the power rule and the chain rule mixed together. So that's going to be negative 1, and then 1 plus 2x. We're going to leave the inside alone, drop the power down, and then we're going to multiply by the derivative of 2x, which is 2. And then we'll do, so I'll tell you what, we'll write that as negative 2, 1 plus 2x to the negative 2 power. And then we'll do the second derivative. Second derivative, we're going to do the power rule again. So it's going to be negative 2 times negative 2, that's going to be 4. And then leave the inside alone. Drop the power down to negative 3. And then multiply again by 2. So that's going to make that 8 times 1 plus 2x to the negative third power. And then we'll take the third derivative. And so our third derivative is going to be negative 3 times 8, which is negative 24. Leave the inside alone again. Drop the power down to negative 4, and then we're going to multiply by the derivative of 2x, which is 2. So that's going to give us a negative 48, 1 plus 2x to the negative fourth power. And that's our third derivative. And so now we need to evaluate each one of these derivatives at 0. But actually, we only need to evaluate the third derivative at 0 because it's only asking us for the coefficient in front of the x to the third term. So we'll save ourselves a little time, and we're going to say what is the third derivative evaluated at 0? Well, if we plug in 0 here, we get 1 to the negative fourth, and 1 to any power is 1. So it's going to be negative 48. And if the people writing this problem were a little bit wiser, they would have put negative 48 as one of the answers because a lot of students are going to stop there. But remember that the coefficient in front of the x to the third term is the third derivative divided by 3 factorial. So we need to take our negative 48, divide it by 3 factorial, which is the same as negative 48 over 6, which gives us negative 8. And the answer is A.